Back to another video, guys. This is all about rotational dynamics. We continue doing this series and we're gonna go through a very typical example of applied physics, and we're going to consider acceleration of falling chimney. Okay, so make sure you remember how to work out basic kinematics for rotational dynamics, okay, like angular acceleration, angular speed, or velocity. So that's the main basics. If you're not sure how to do that, please watch the video before. The solution obtained for this problem can be actually expanded to a wide range of problems with the same character and with the same scenario, okay, where actually rigid body can be modeled as the thin rod. So that's an idea, and that's key idea, okay? So make sure you remember how to calculate the moment of inertia for thin rod. If not, again, try to watch my video where I explain how to work out moments of inertia of different rigid bodies, like rings, wheels, thin rods, and so on, okay? So make sure you know that. And in case if the rigid object is different in shape, probably it's not a thin rod, or probably cylinder, maybe, I'm not sure. So cylinder, if it's tall cylinder, it fits up the thin rod, but I mean, it's something different in shape, okay? So make sure you can work out the proper moment of inertia. And this is the only adjustment you need to make within other parameters. Input parameters stay the same. Okay, so let's go to the problem. I think that's definitely, it's sort of challenging physics. If you're a student of A-level or B, so that might be hard for you, but it's worth to pay time for that in order to get those basics, and also with advanced formula, with advanced, explanation, and just get deeper into the problem, okay? In this case, you'll be really get well with rotational dynamics, okay? Let's have a look. Pause the video. As always, try to do by your own. Here is the figure, and there is also another last question there, D. When the chimney falls, it often breaks somewhere along its length during the fall before it hits in the ground, okay? Shown on the picture, you see this actually rupture happens there, okay? That's breakdown there, okay? That's long before it hits the ground, okay? And you need to explain why it happens. Okay, so let's get to the first question. We need to find the angular acceleration and angular speed of the chimney when it's at angle theta to vertical during its motion. Okay, let's say this is the thin rod that can be modeled, or chimney can be modeled using the concept of thin rod. Okay, that's very significant. And also make sure that you understand what's happening actually. Here is the position at time t at the angle theta, so I mark this angle as theta, okay? And I also depict the trajectory for the center of mass. That's really significant because we cannot, we need to choose some point that we need to keep track on, right? And of course, for different points, they will have different passes, different linear velocity. However, angular acceleration and angular velocity omega stays for all points the same. That's key concept here, okay? So that's the center of mass, cm, and when it's at angle theta, center of mass is right there at this point. So we need to figure out the angular acceleration and angular speed of that. How to do that? Where is the starting point? So I recommend to consider first of all forces. Let's draw up the Freebody diagram. So what sort of force we have? Definitely at this, so we are going to consider position 2. So that's position 1, and this position 2, we are going to consider all force acting at the moment when the rod is, or chimney is at position 2. Okay, so we put the gravity force down, definitely apply to the center of mass. So we apply mg here, and the angle It's also going to be theta, okay, right there. So this angle is theta, so that's why this angle also theta, if you like. Okay, next part. We definitely know here is the base, and we definitely know that to the base there is a normal force acts always perpendicular to the surface, not perpendicular to the chimney, right? I mean, not along the chimney when it's at position 2, but somehow like vertically, still vertically, okay? So what it means that we can mark this vector force as N, and this is mg, okay? And friction force. But let's have a look at the words and the statement here. It starts forming over when its base is ruptured and there is sufficient friction, okay, at its lower end. So what does it mean? It means that it doesn't slip up, okay? It means that point's still fixed. It like just simply rotational dynamics. No any translations happens, okay? So that means that's pure rotation, okay? And the pivoting point is right there. So I just mark that as the pivoting point. Here is the pivoting point. Pivot, okay? And what we're gonna do right now, of course we need to put a friction force as if so. Let's pretend that there is no friction. What in this case? So obviously this point at the lower end will have a translation of motion to the left side, right? So that means friction, if in the case of friction, it will oppose to that motion, and that means it's going to be directed this way. So that's the friction, not friction force. Okay, so we set up all forces. We draw this free body diagram. That's necessary definitely for following steps. And right now we are going to start from energy conservation. We keep track on the center of mass. And let's just simply describe what's happening in terms of energy. So we're going to use, so for the question A, we're going to use work energy theorem about how one type of energy is converted into another one. Center of mass was at this height, and we can say that the total height, let's set up the total height as h, okay? So that's the total height here. It's going to be h. It's the total height. And we have to keep track of the center of mass. Assuming that your chimney is a uniform, that means the mass evenly distributed in the volume of the chimney, we can say that center of mass has a position of half of the height, right? So that's the starting position. So that means potential energy is going to be at the position 1, EP, and as normally we calculate it, potential energy in the starting point is going to be mg h/2, okay? So what about at the position 2? So position 2 corresponds to another potential energy, which is right there, and this is potential energy in the position 2. So what about the height? So the height definitely is lower, so that's why potential energy in the position 2 is lower than in the position 1. So that means part of the energy goes into other type of energy. Definitely is going to be rotational kinetic energy. But hold on, let's rewrite at this level. We're going to have this height, and this height can be calculated as if you subtract mg, and as if you subtract from, so let me see, it's going to be the cos, yeah, I think, yeah. So this is height, so we're going to consider this small triangle with the hypotenuse to be equal h/2, and what we're going to calculate is this H2 in the position 2, which is going to be the adjacent side in this triangle. So that means it's going to be mg h over 2 cos of theta, okay? So right now, what we're going to have the change in potential energy, which is simply potential energy in position 1 minus potential energy in position 2. We'll simply transfer it and goes into kinetic energy. So kinetic energy of the rotation. If you write that, you'll definitely know that kinetic energy is simply at the position 2, of course, yeah. That's going to be mv squared over 2, but this is for the particle, right? For the particle, we know that v is omega r. That means if we write in this way, we can say that kinetic energy is going to be equal to m omega squared, better to write m r squared, okay, and also omega squared over 2. But let's have a look at this value. So what can you see there? M r squared. That's definitely moment of inertia for single pointary mass at the distance r from the rotation. Okay, so in our case, moment of inertia should be for the center of mass of the, basically that's going to be the moment of inertia for the rod, right? And completely, right, for the whole rod. So that's why make sure you remember that the value for the moment of inertia for the rod with the length or height h is going to be defined as mh squared over 3 instead. So that means we just simply swap, instead of mr squared, we're writing mh squared over 3. There's going to be kinetic energy of the rod rotating around pivoting point, which is right there at the lower end of the chimney, okay? So what we'll have finally? We'll have finally the following, that we've got mg h over 2. Because we have the difference, we simply use that as the common factor, and right now we can leave 1 minus cos theta, okay? So what we have on the right side? On the right side, we have moment of inertia, which is mh squared over 3. So simply kinetic energy, we can write another way around. So that's going to be I omega squared over 2, okay? So that means right now we can plug this expression for the thin rod. So that's fair for the thin rod, okay? And we will get the following. So we'll get mh squared omega squared over 3 and times 2, okay? So that's what we exactly need in order to get the expression for omega. So let's cancel for a while. Let's cancel for a while, just probably expand a little bit, okay? And we will have the following. So mass will be cancelled. We'll have g 1 minus cos theta is equal to h omega squared over 3. From where we can express omega, all right? So let's express omega as the square root of 3g over h, and we will have 1 minus cos theta. And let's analyze for a while. So that's the final expression for the omega, so I just rounded up. According to what we are supposed to do, we need to define the angular acceleration and angular speed. Right now, we've got the angular speed, so that's angular speed. So we define that value. Let's analyze for a while. So omega definitely depending on theta, but it stays fair. It stays the same for every single point on the road, chosen on the road. So no matter for the top, for the center of mass, or even for the bottom part. So omega is the change of theta over time, okay? So I explained before. Next, if theta goes up, what's happening with omega? So cos theta, the more the angle, the less cos theta goes to 0. And 90 degrees is going to be 0. So what we might say that omega is still increasing. And that's the truth. It starts falling and it's accelerating, okay? So that's fair dependency, omega from time. Let's move next. We need to define angular speed. We define that, and we need to define angular acceleration. So, where's the connection, angular acceleration and the angle? For this reason, I will hire the idea of the torque. So, as we explain, what force? One more time, I'll just direct forces using the Freebody Diagram one more time. So, that's reaction, that's friction, and that's the gravity force, okay? Right now, I want to say that the distance from the pivot to mg is going to be that, okay? It's going to be half of the length or half of the height. So this is mg, this is the friction, okay? That's the friction force, and this is the normal force. Okay, so we'll get the idea of the torque. But first of all, let's remember the second Newton's law. I'll show you quick how we can get actually a second Newton's law for a while. I just zoom in and let's just remember. So second Newton's law tells you that if we have tangential force, for example, tangential force to the path of the motion for any random point. Let's suppose we choose the center of mass, okay? So we are going to apply tangential force. So tangential force in this case, for example, for the gravity force, is going to be that. So that's the tangential force. I mark as F tangential, okay? So that's F tangential force. It's going to be equal to ma tangential acceleration, okay? So tangential acceleration directed in the same way. Let me mark as the pink one, okay? So that's going to be tangential acceleration. So a tangential. All right. If we apply both sides by the r, which is going to be the distance. Okay, so we multiply both sides by r. There's going to be a distance from the pivot, to the pointary mass that we keep track on. We'll get the following: r times f tangential is going to be equal to ma tangential and times r. Okay, so we multiply both sides by r. But this is what is known the moment, okay, or the torque. Actually, so this is the torque. So at the shortest distance from the pivot to the given point where the force is applied, multiplied by the force, okay? So the shortest distance is the distance r to actually tangential force. So you probably remember that if you're given like some force, not necessarily tangential to their path of the motion, you can multiply by r and times their, let's say, the sine of the angle between them. But so that's typically the same as you taking tangential force and multiplying by the distance along your rigid body from the pivot to your given point, okay? So that we're going to use there. On the right sides, tangential acceleration, just remember, is change in the linear speed over time, right? But linear speed can be expressed through omega, right? So that's why it's going to be change in omega over delta t times r, okay? But change in omega over time is going to be angular acceleration. So here how we can find the angular acceleration there. That what we're looking for. So this is alpha. Remember kinematics, it's all about that. So angular acceleration. Okay? So what we're gonna do, we're gonna just rewrite that tangential acceleration is equal to alpha r. So that's why here we are going to have m tangential acceleration alpha times r squared. Okay? So that's why we are going to have m alpha times r squared. But again, we are keep track on the pointer mass. So that's why we can rearrange m r squared as the moment of inertia for a given mass. So that's why we'll get more general equation for the torque. So it's I times alpha, okay? Moment of inertia times alpha. That what stays for the torque. In our case, it's not the pointer mass, it's the thin rod, so that's why the moment of inertia is modeled using the idea of mh squared over 3. So that's the formula that you can get by applying calculus or applying integration, okay? And what about the torque? The torque is simply, in our case, as the force, which is the gravity force, mg, times, because we need to define tangential acceleration, we actually need to times, if we consider this angle as theta, and this is going to be a tangential component of mg, is going to be mg times sine of theta, okay? And times r. In our case, r is equal to h over 2 because we keep on track of center mass, okay? So that's why we'll get multiplied by h over 2. Okay, on the right side, that's going to be the moment of inertia times alpha. So that's why we'll get, on the right side, we'll get mh squared over 3 and times alpha. It's almost the last step. It's almost the last step because right now we are on the way of finding alpha. So our goal is to find alpha. So how to find alpha? Alpha from there is 3g over h sine theta. Okay? And over 2. Yeah. So exactly that what we are supposed to have. And again, let's analyze dependency on the angle. So alpha angular acceleration from the angle. So angular acceleration. The more theta here, okay, that's the angle theta, the more actually alpha. And as we are supposed to have, right? The more angle, the more acceleration. That's fair. So alpha will have the same formula for any point again as the angular speed or angular velocity. It will have the same value for the center of mass, for the top, and even for the bottom one. Okay? So solutions for questions B, C, and D you might find in the next video. I decided to split on 2 smaller parts because the first question A was pretty, extended, and that's I showed you several like techniques and also derived formulas. So that means it takes pretty a lot. Okay, but however, it's more about details there for better understanding. So if you like that, please like this video and see you in the next episode.